Hello class, in this lesson we will learn how to calculate formal charge in Lewis structures, and we will also learn how to apply that to polyatomic ions. During the course of this lesson we will learn how to draw polyatomic ions. It requires only one additional step compared to drawing a normal Lewis structure. So first, to frame our lesson, I wanted to take some time to do this warm-up where we draw selenium dioxide, SeO2. So I recommend pausing the video now and working on this problem, and then when you are ready, you can unpause and we can continue. All right, I'm going to work on my approach for this particular problem. I first know I need to calculate the total valence electrons. So I know that Se is in the same column as oxygen. So I have one Se atom times 6 valence electrons plus 2 oxygen atoms times 6 valence electrons, which means I have 18 electrons in total to work with. 6 times 2 is 12, plus 6 electrons from the selenium gets me 18. So I know that the least electronegative element is going to be in the center. Selenium is further down the column. Remember that electronegativity increases as you go up and to the right. So as you go across a row to the right, it increases. As you go up a column, it increases. Since selenium is further down on the column, that is the least electronegative. I'm going to put selenium in the center and connect it to my 2 oxygen atoms. I'm going to use a method that does not follow common bonding patterns, but make sure that all atoms have 8 valence electrons at the end of the problem. Currently, I have used 4 of my 18 valence electrons, so I can subtract the 4 that I've used. I have 14 left to work with. So I'm going to start on the outside and work my way in, adding electrons in pairs until each atom has 8. So 2, 4, 6 plus the line makes 8. 2, 4, 6 plus the line makes 8. Selenium has 2 from one line, 2 from the other line, so it needs 4 more. All right, so I have my structure here. I need to double check. Does everybody have 8? Yes. Does the number of electrons I drew match the number of electrons I have available? Well, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We actually need to take away a pair here. Now we have 18 electrons for everyone, but our issue is our octet rule is not satisfied. So we need to make a double bond. We can make a double bond by taking a lone pair from an atom that does have 8 and sharing it with selenium. So I can take a pair from this oxygen on the left or a pair from this oxygen on the right. How do I know which one to take from? Well, the answer is you don't. So let's go ahead and just take one from the left and we'll see what happens. All right, we formed a double bond. All I did was take an existing pair and turn it into a shared pair. We still have 18 electrons for the entire molecule, and everyone now has 8. Now, there's really no reason why I chose to do it. Take the lone pair from the left side. You could have taken the lone pair from the right side. So let's show what that would look like if we had done that. Oops, computer glitch on me, sorry. There we go. So we'll go back, get set up so we were in the same format as before. All right, And we said we're going to take a pair from the right side this time and turn it into a double bond. All right, so what's interesting is these molecules look like mirror images of each other. Okay, believe it or not, there's also a third way you can draw this. If you are someone that follows common bonding patterns, we know that oxygen normally has 2 bonds and 2 pair. The 2 structures we've drawn so far only obeys that common bonding pattern for one of our oxygens. So, what would happen if we gave each oxygen 2 bonds and 2 pairs? Well, I see that the octet rule is satisfied for everything, but my issue is I have 2, 4, 6, 8, 10, 12, 14, 16 electrons. I need to add 2 more somewhere. Well, oxygen's in the second row. It cannot take on any more additional electrons, but selenium is in the third row and below, which means it can have an expanded octet. So if I have extra electrons, I can add them to selenium. Now, you'll notice selenium now has 10 electrons. Remember, certain elements, when they are in the center, can have an expanded octet. So in this case, we're allowed to put this extra 2 electrons on selenium. And when we do it this way, we obey the common bonding patterns that we saw for oxygen. Now this means we have 3 correct structures here. How do we know which one's the best one? Well, that's going to lead us into formal charge. So what is formal charge? The best possible Lewis structure has the fewest number of atoms with a formal charge, which means we have as many neutral or zero charge atoms as possible. If the overall molecule has a charge, such as in a polyatomic ion, which we will explore in a little bit, the formal charges on each atom add up to the overall charge. Typically, formal charges other than -1, 0, and +1 are uncommon. Sometimes a +2 or -2 may be seen, but typically the charges are always -1, 0, and +1. To calculate formal charge, we need to determine the number of valence electrons an atom should normally have based off of its position on the periodic table. Then we're going to count the number of non-bonded electrons, so basically the number of dots that make up the lone pair. And we're also going to count the number of bonds that the atom has in the Lewis structure. A double bond will count as 2, and a triple bond will count as 3. The formula for formal charge ends up being the valence electrons minus the number of bonds minus the number of non-bonding electrons. We're going to apply this to the warm-up that we just did because we have several different atoms here that we want to explore. So I'm going to try and color code. We've got Se, and we've got an oxygen with a double bond on one side. We've got an oxygen with a single bond and 3 pairs. And selenium has, a lone pair in the middle. There we go. All right, I'm going to draw the same setup on the other side. So here we go. This time it's the one on the right with the double bond and the 2 pair. And then the one on the left with the single bond and the 3 pair. And then the last one I have to draw is selenium. And this is the one where we had the double bond for both oxygens, and we followed the common bonding pattern. All right, so now that we have them set up and they're color-coded, we're going to calculate formal charge for each one. So for the green oxygen, oxygen normally has 6 valence electrons. In this structure, it has a double bond, which I count as 2 bonds. And it has 2 lone pairs, which means 4 electrons. So I'm going to subtract 4 electrons here because there are 4 dots on that particular oxygen. 6 minus 2 is 4. 4 minus 4 is 0. There is a 0 formal charge on the oxygen. I'm going to repeat the process for selenium. Selenium also normally has 6 valence electrons. Selenium in this structure has a single bond and a double bond, which is 3 lines total, or 3 bonds. So I'm going to subtract 3. And then there's 1 lone pair, or 2 electrons, so I'm going to subtract 2. 6 minus 3 is 3, minus 2 is a plus 1. The oxygen here, 6 valence minus 1 bond minus 3 pair. There are 2 electrons per pair, so we're going to subtract 6 because there are 6 dots total. 6 minus 1 is 5. 5 minus 6 is negative 1. So interesting. The oxygen on the far right has extra electrons than normal and deviates from the common bonding pattern, so it has a minus 1 charge. Selenium has fewer electrons than normal, so it deviates from a common bonding pattern and has a plus 1 charge. Let's do the calculation for the remaining atoms. 6 minus 1 minus 6. Interesting, this time the oxygen on the left has the minus 1 charge. 6 minus 3 minus 2. Selenium has stayed the same. And then for the final one, 6 minus 2 minus 4. Interesting. So it looks like because the double bond and the single bond switch places in this structure, the formal charges also switch places between the oxygens. Let's take a look at the last one. On the last one, I have 6 minus 2 bonds minus 4 dots, which gets me 0. Selenium is 6. This time it has 2 double bonds, which means we're going to subtract 4, and it has 2 dots from the lone pair. Well, interesting, that's also 0 now. That's a change from last time. And then for the final one, 6 minus 2 minus 4, also 0. So circle the structure of SeO2 that is the best. Well, remember it says the best one is the one with the fewest number of atoms with the formal charge, so as many neutral or 0 charge as possible. These structures that we drew first are still valid structures, but they are not the best structure because they don't have all of the atoms as a 0 formal charge. So this structure that we drew, even though it has an expanded octet and breaks the octet rule in that regard, is a better structure because the formal charge is 0. Okay. One thing I want to add to this, typically negative formal charges go on atoms that are more electronegative. Notice that when we calculated our formal charges for these first two, the negative was on oxygen, where we had a more electronegative atom, and the positive was on selenium, where we had the less electronegative atom. This is not always the case, and you'll see this in a couple of the practice problems below, but sometimes, or most of the time, we should strive to have the electronegative or the formal charge be on the more electronegative atom. There are, of course, exceptions, and you'll see some of those in play here. I recommend going through and practicing calculating formal charge on this sheet before moving on to polyatomic ions. I would pause the video now. Okay, welcome back. I'm not going to go over the answers in this video, but if you would like some support, come see me for additional help. We're moving on to polyatomic ions. So the nice thing about polyatomic ions is that it will help us directly apply what we just learned about formal charge. What is a polyatomic ion? A polyatomic ion is a stable covalent compound that has an overall ionic charge. The charge actually helps to make the polyatomic ion more stable. Some conventions that we use when we draw the Lewis structures for these polyatomic ions, we put brackets around them and we place the charge on the outside of the brackets. The key bit of information here that changes how we look at the total number of valence has to do with the charge. Remember that a negative charge means I've gained electrons, So if I have a negative charge for my polyatomic ion, I need to add those number of electrons to my total valence. If I have a positive charge, that means I have lost electrons, and I need to subtract that charge from my total valence. Let's do an example. Nitrogen normally has 5 valence electrons. So this is nitrogen. And then I have 4 hydrogen present times 1 valence electron. When I do this math, I get an odd number of electrons. That is problematic because I know that I need to satisfy my octet rule, which means 8 electrons. Anytime I have an odd number of electrons, something is usually wrong. So one thing I notice is there's a positive charge here. When I have a positive charge here, I subtract that 1 electron that was lost to make up for the positive charge, and I can get an even number of electrons. So I have 8 electrons present in this molecule because I subtracted the electron that was lost to give me the positive charge. Now I can go up and set my Lewis structure like normal. I know that I'm going to have to attach my 4 hydrogen atoms. And when I do so, 2, 4, 6, 8 electrons, because 2 per line. This is a complete and valid structure. All I need to do is brackets and then place the charge on the outside. Now, one thing you'll notice, I will calculate formal charge for hydrogen, but this is the only time I'm going to do that, and you'll see why. So for hydrogen, hydrogen normally has 1 valence electron, it has 1 bond, and it never has any lone pairs. So the formal charge for hydrogen is 0, and it is always going to be 0 because it can only have 1 bond. So for that reason, I usually don't ask students to calculate the formal charge on hydrogen atoms. You may have noticed this when you did the practice. For nitrogen, however, we typically have 5 valence electrons, minus 4 bonds, and no lone pairs, which means we have a +1 formal charge on my nitrogen. One of the things we have to recognize is that the formal charges in the atom or in the molecule will add up to the overall formal charge. So since I have a +1 charge overall, I can expect that one of my atoms will have a +1 formal charge. Let's repeat the process with cyanide. We have Cn minus. So I have 1, oops. Sometimes my screen glitches out, I apologize. Problems with using a touchscreen device. All right, so 4 valence electrons for carbon. Plus 5 valence electrons for nitrogen. And you'll notice again, we're going to have a similar issue to this last one. We have an odd number of electrons here. So remember, I see a negative charge. If it's a negative charge, I need to add the number of electrons from that charge because that indicates how many extra electrons we've gained. It's a 1 minus charge, so I'm going to add 1 electron. If my my stylus will cooperate with me here. There we go. So this time I'm adding an electron because it's a -1 charge. If it was a -2 charge, you'd add 2 electrons. If it was a -3 charge, you would add 3 electrons. Here I get 10 electrons total to work with. I'm going to go ahead and make my structure here. I've used 2 of my 10 electrons, and I'm going to start on the outside, make my way in, make sure everything has an octet. So 2, 4, 6, 8, 10, 12, plus the line makes 14. This does satisfy the octet rule, but I have way too many electrons here. So I should erase some. And now I have 2, 4, 6, 8, 10 electrons present. The problem is the octet rule is not satisfied for either of my atoms, which means I need to take a pair and share. So I'm going to take a pair, and make a double bond. All right, by doing that, I now have 8 electrons for carbon, satisfying the octet rule, but nitrogen still only has 6. So I need to take another pair, and this is going to make a triple bond. Now I have 10 electrons total, 2, 4, 6, 8, 10, and each atom has 8 electrons, 2, 4, 6, 8, 2, 4, 6, 8. The last thing I need is my brackets. There we go. I need my bracket, and then my charge goes on the outside. All right, I can calculate formal charge. Carbon normally is 4 electrons minus 3 lines or 3 bonds from the triple bond, and minus 2 electrons from the lone pair because there are 2 dots. 4 minus 3 is 1, 1 minus 2 is -1. Nitrogen has 5 valence electrons, minus 3 minus 2, and this is a 0 formal charge. So this is an interesting example where the negative formal charge is actually not on the least, or not on the most electronegative atom. It is on the least electronegative atom. Again, this happens from time to time. There are exceptions, but typically when we draw molecules, if there's a formal charge that's negative, it should be on a more electronegative atom. But so far, we've seen a bunch of examples where that deviates from our known rule or pattern. Okay, a couple of things about exceptions to the octet rule just to remind you about. Some things you may encounter in the future. Some molecules may end up with an odd number of valence electrons, making it impossible to have an octet. An example of this is NO. These are referred to as free radicals or radical molecules, and you won't really see them in this course, but they do exist. So for the purpose of our chemistry course, if you see an odd number of valence electrons, you probably calculated something wrong. There are a couple that exist with odd number of valence electrons, but I will not give you any of those examples as problems that you will have to draw. As a reminder from the beginning of our lesson, some of our central atoms can have more than 8 electrons due to having extra electrons in the d orbital. Those elements, when they are in the central atom, they are in the third period or higher. We know that additional lone pairs can be added to those central atoms, or more bonds can be formed. The goal of this is to reduce the formal charge. And when you go through the practice today, you'll see that there are a couple of structures given to you in which you have to calculate formal charge, and then you need to tell me which one is the best one based off of formal charge. So expanded octets are a way for us to reduce formal charge. All right, there's some built-in practice at the end of this document. Here we go. And that is all for this lesson. I will see you in the next one.